Let's start with a quick overview of the discrete Fourier transform. So the discrete Fourier transform is a tool for converting a sampled signal, initially expressed in terms of measurements at sampled points, as in a list f at 0, f at 1, f at 2, etc., to one expressed instead as a linear combination of basic waveforms of varying frequencies. Let's be a little more precise and fix some notation. So we're going to assume that the signal that we're looking at is periodic with some given period n. And so we can read off our sampled points as a list of the form f at 0, f at 1. We're only sampling at some discrete time intervals, which we'll think of as integer points, f at 0, f at 1, f at 2. And we're going to imagine that this is periodic with period n. So by the time we get to f at n minus 1, we've actually read off all the important information about this function. That is to say, if we were to again sample at time n, we get the same answer at time 0. If we were to sample at n plus 1, we get the same answer at f of 1. So for intents and purposes, we can think about the information of our sampled function as a vector whose coordinates are the measurement at 0, the measurement at 1, etc. Of course, when you express a vector as a list of numbers, implicitly you've chosen a basis. And so it would serve us well to take a closer look and see what that basis is. To be a little more explicit here, by writing our function as this particular column vector with this set of numbers, what we're really saying is that it's f of 0, the first coordinate, times the standard basis vector with a 1 in the first coordinate and 0 elsewhere, f of 1 times the 1 in the second coordinate, etc., all the way up to that one. And so if we give these guys the names, this should naturally be called, we could call it E0, because we're kind of labeling this as the 0th coordinate, E1, etc., up through En minus 1. Then folding this process backwards, we can again think about these vectors, these basic basis vectors, as themselves sample functions. What sample functions are they? Well, E0, for example, is the thing which at time 0 gives the measurement 1 and all other times gives the measurement 0. More generally, ek of j is 0 if j is not equal to k, and 1 if j equals k. And so what we've really done in this, by expanding our sample function in this way, is write an arbitrary sampled function in terms of these special sampled functions, e sub k. Now, this is a very natural basis in the sense of measurements because the coefficients of our vector in this basis are exactly the measurements. So this is a very natural way to write our vector representing our sampled function. But it's going to be useful for various applications to use a different basis where the basis vectors represent particular sampled functions called waveforms. So let's talk a little bit about what these basic waveforms are. So the idea is that the basic waveforms represent sampled functions whose measurements give back complex numbers of unit length, that is, complex numbers that lie in the unit circle in the complex plane. As time moves forward, these waveform measurements rotate about the origin. That is to say, at time 0, maybe at time 0 they'll be sitting on the positive x-axis. At time 1, they'll have rotated by an angle of theta in the counterclockwise direction. At time 2, they'll make an angle of 2 theta. At time 3, 3 theta, 4 theta, 5 theta, etc. So that once you get to time n, where the signal repeats, you've gone through some integer number of full rotations and returned back to the x-axis. Now, because of trigonometry, what that means is that at any given time, if you looked at the real or imaginary parts, this would be described by sines and cosines of these angles. And so you can also describe these basic waveforms in terms of sines and cosines, at least the real and imaginary parts. So how would we express these waveforms with complex numbers? So as we were saying, the basic idea is that at time 0, these basic waveforms would be sitting on the positive real axis at a unit length. At time 1, it's making some angle of theta, again on the circle of unit length. At time 2, it's making an angle of 2 theta, and as time moves on, these revolve around the origin. These particular complex numbers have a nice representation, and that is the so-called polar form. So this particular complex number is actually described by e to the I theta, the complex exponential function. This thing is described as e to the I times 2 theta. And of course, this thing is e to the I times 0 times theta, which is, just 1. E to the 0 is 1. Altogether, what we're really saying is that at time t equals k, our signal is gotten by evaluating e to the I k theta, which I could write as e to the I theta to the k. And this is going to be a more convenient way of writing it. That is, these waveforms in general are going to be described as at time, so we're going to call them e sub, an example will be to take a function which at time k spits out rho to the k, where rho is going to be some complex number of this form for some e to the I theta for some theta. Let's finally actually examine the particular waveform basis. The first waveform, E0, is going to be a wave that doesn't actually rotate. It rotates, so to speak, at speed 0, which is to say it just sits on the positive x-axis at 1. This is the signal which gives a reading of 1 for all times j. The waveform E1 is going to be the kind of basic wave that goes around exactly once after time n. So this is going to have the form omega to the j, where omega is some complex number sitting at an angle of theta, and what should theta be? Well, when you do that rotation in times, you need to get back to the origin. So theta has to be 1/nth of 2 pi. So it has to be 1/nth of the way around the entire circle. What would E2 be? E2 is going to rotate around twice as fast as E1, and so we could think of it as omega to the 2j instead of omega to the j. So when j goes up by 1, the angle goes up by twice this theta instead of once this theta. You could also read this off as omega squared to the j. In other words, it uses the complex number omega squared instead of the complex number omega, etc. So that in general, if I were to say e sub k, and say what does that do at the jth sample point, this is going to be omega to the jk, which I could also think of as omega to the k. That tells me which of these complex numbers is creating the first basic angle, and then to the j, how many times I've done that basic rotation. All right, and now you can see that the k is somehow telling you after you get to time n how many times you've gone around the circle. That's at least the right idea for small k. So that is to say, we can interpret this as e sub k goes around for k rotations by time n, at least if k is not more than n over 2. If k is more than n over 2, it actually just looks like you're rotating around backwards. So if you play with these complex numbers, you're really looking at a negative angle. You could think of it as a negative angle more concretely instead. So this is really, these e sub k's are going around in the opposite direction. N minus k times. At least, so for k bigger than n over 2, it just looks like you're going around It kind of slows down again as k gets bigger instead of speeding up, but going in the opposite direction. Okay, so those are the basic waveforms. And now we finally come to the discrete Fourier transform itself. It turns out that these basic waves that I've just described form a basis for the vector space of these sampled signals. And what the Fourier transform is it's a tool for going between the two bases, for going between the standard basis and the wave basis. That is to say, if you wanted to change from one basis to the other, this is given by a so-called change of basis matrix. And it turns out that the change of basis matrix has the form 1 over n is the number of sample points, f sub n, for this particular matrix f sub n. F sub n is called the Fourier matrix. And its entries are easy to describe. What are they? So the jkth entry of the Fourier matrix, well, now actually we have a little bit of a convention that we're going to break with indexing. So generally speaking, when you talk about the entries in a matrix, you number the entries, the first entry, the second entry, up through the nth entry. We're going to use the computer science convention and actually label things from entry 0, entry 1, entry 2, etc., up to entry n minus 1. So we're going to count from 0, we're going to let j and k range from 0 up through n minus 1. And if you do that, you have this nice expression that the jkth entry is omega to the minus jk. If we used the standard notation, we would have gotten omega to the minus j minus 1, k minus 1 if I'd let j start, if I'd said that j should start at 1 instead of at 0. But let's not do that. Okay, so this is the Fourier matrix. And this describes the change of basis. So that is to say, and we have a little more notation to describe. So, so we have this following notation. If you take your original signal, f0 through fk, through fn minus 1, you take this vector, and so what happens when you apply the Fourier matrix to it? So you get some new vector whose coefficients are called f hat of 0, f hat of 1, all the way up to f hat of n minus 1. The entries in this vector are called the Fourier coefficients. So these are the Fourier coefficients. And this matrix F that goes from this vector to this vector, this matrix F, is called the Fourier Transform. So the Fourier Transform, it's not exactly the change of basis, it's off by a factor of n, but it's the hard work involved in changing bases from the standard basis to the wave basis. So just to be concrete here, what we've really said is that there's this matrix whose entries we've described, this Fn, and it has the property that, when you apply it to this, we call the new coefficients these hats, and it has the property that if you have your original signal f, which you've written in terms of the standard basis, as we've done before, then you can actually rewrite it in terms of the wave basis, where the coefficients are 1 over n times the Fourier coefficients times the corresponding waves. So these are all from k equals 0 to n minus 1. That's how we're doing our indexing. Okay? And so what this says is that these coefficients obtained by applying the Fourier transform, this Fourier matrix, give you the bulk of the work in describing how to take a signal and rewrite it in terms of the wave basis. So we have two basic interpretations of the Fourier transform. On the one hand, we have the abstract interpretation as it relates to changing the basis. Oops, excuse me. That is to say, if we express our function in terms of the standard basis in this way, the Fourier coefficients divided by n express our function in terms of the wave basis. So that's the interpretation as it relates to the change of basis. Also, we have a very concrete expression, which is because we actually know how to write down the entries of Fn in terms of these powers of roots of unity, if you work out the actual matrix multiplication to go between this vector and multiply it by this to get that, then you get the, when you just do it, you get this following expression for the kth Fourier coefficient. It's this particular sum of the roots of unity that come across that, what do we call it, the kth row, and then multiplying things by that vector. It looks like this particular expression is what we get for the Fourier coefficients. So let's just quickly use that and work out just some really very basic examples. So like, what if I took the standard basis vector EL, let's say, and I said, what's its Fourier coefficient, what's its K Fourier coefficient? In this way, the vector EL, or the signal EL, is naturally expressed in terms of this basis as the thing with just a 1 in the Lth slot. And so we can use this formula. This is more attuned to writing to the fact that EL is already written in the standard basis. And we get this expression, sum j equals 0, n minus 1, omega to the minus jk, and then the signal EL evaluated at j. Okay, what happens if you evaluate EL at j? You usually get 0 unless j is equal to L, in which case you get 1. So every term in this sum is 0 except for the term where j is equal to L. So you actually get omega to the Lk as the only interesting term, EL of L, which is actually just 1. And so the answer is, this is given by omega to the minus Lk. Okay, now let's do the slightly counterintuitive thing of doing the Fourier transform to one of the basic waves themselves. To do this, so if I'm looking at the Fourier coefficient of EL, to do this, it's more natural to use just the interpretation of what the Fourier transform is. We know how to write EL in terms of the wave basis. So, so if I'm trying to work this thing out, EL of k, well, we know that EL in the wave basis is 0 times E1 times E0 plus 0 times E1 plus all the way up to, when I actually get to EL, just 1 times EL, and the other ones are zeros. You know, zeros up to there and zeros beyond. But the expression in terms of the wave basis tells me what the Fourier coefficients are. So that is to say, I also know that this is equal to f hat of 0 divided by n E0, f hat of 1, blah, 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 and over here, f hat of, this was, f hat of L divided by n, EL, and then etc., all these things. And so what does that tell me? That says that, oh, what did I write? F. The F that we're looking at is E sub L, right? This is E sub L, excuse me. E sub L of 0, E sub L of L, hat. Okay. So what does that tell me? That says that all of these E sub L's are 0 except for E sub L hats, except for the E sub L hat of L. So this is equal to 0 if k is not equal to L. And now, what do I know about E sub L? I know that, or E sub L hat, I know E sub L hat of L. If I divide by n, then I get 1. So that says that E sub L of L is actually n. The E sub L hat of L is n. So the Fourier coefficients of the basic Lth waveform itself are 0 for k not equal to L, and the nth thing has coefficient n. Right, that's what you want. You want, if you divide by n, you actually get the coefficient in that basis, which is 1.